Alright, so this is the final examinations for semester 2, sessions 2022 and 2023. Okay, it has also two parts. Part A is the objective questions and part B is the subjective questions. So let's look at the first questions. Okay, so the parallel metal plate of capacitors, right? So this is a capacitors. So parallel metal plate of capacitor look like this. Okay, is separated by means that want you to define, okay, what is the material in between the capacitor. So the answer is insulator, okay, or dielectric. Next, okay, the capacitance between two parallel plates decrease with, okay, so this is the capacitance of parallel plate. So it's equal to, C is equal to epsilon S over D. Okay, so this is the equations. We look at the statements. The shorter plate area, okay, plate area is the S. Okay, shorter plate area means smaller, and larger distance between them, D increase. Okay, so the capacitance between two parallel decrease. Decrease means become smaller. Okay, so smaller is when the S decrease and the D increase. Yeah, this is correct. Okay, shorter plate area, okay, and higher applied voltage. Voltage. Okay, it doesn't relate to the voltage, the capacitance. Larger plate area, okay, shorter distance between plates. Okay, if the distance is shorter, smaller, okay, C will increase. So this is not correct. So larger plate area, okay, long distance between the plate, okay, and higher applied voltage. This is also wrong. So the answer is A. Okay, next one. So you have so many capacitors and they are arranged in parallel to each other. Parallel, what is the meaning of parallel? This is the parallel configurations. Parallel. Okay, parallel. Okay, so you have so many capacitors, 4 capacitors. Okay, parallel. So what is the total capacitance? So for parallel configurations, the total capacitance will be the summations, means 5 plus 10 plus 11 plus 50, 6, 76. So answer is C. Alright, this one is the question from the module. Alright, question from the module. So consider the cross section of two spherical capacitor as shown in the figures. Okay, or with all these dimensions, it is exactly the same as the questions in the module. You can refer back the solutions. Okay, so in this case, the answer is B. Okay, it's B. Just follow the answer in the module. Alright, I think this one also, question number 5 is also question from the modules. So you can try it out, find the capacitance, okay, and refer back to the steps that we have gone through before. Okay, so the answer is A. Right, we look at question number 6. Okay, so it is a conducting triangle loop of 10 ampere. Okay, so this is the I, located in Cartesian coordinate system. So determine magnetic field intensity at 0,05. Okay, so 0,05 means at the top, okay, at the top, 0, 0, 5 due to side 1 of the loop. Okay, where is side 1? Side 1 is just this line, okay. This is the side 1. So if you view this thing in 3D, okay, the drawing will be something like this. You have axis Z, Y, and also the X. Okay, so your side 1, your side 1 will be from here until here, alright. Okay, so the length is 2, okay, current, and you are required to find the magnetic field at 0, 0, 5. Okay, so this is what you need to find out. So for this question, you need to apply the formula H equals to I over 4 pi r. Okay, then you have a cos alpha 2 minus cos alpha 1. Okay, so this is the formula that you have to apply. Okay, so let's find the answer for this H. Okay, so first of all, we need to find out what is the R. Okay, so the R is the distance, okay, from the line, the blue current elements. Okay, so first of all, we need to find out what is point T. Okay, so what is point T? So in this case, our point T is 0, 0, 0. Right, so our R will be 0, 0, 5. The observation point minus the point T. Alright, so we will have 5 Z. Okay, so the R, the distance, will be 5, and the unit vector R will be Z. Okay, next one is to find the alpha 2 and alpha 1. So we can zoom in here. This one will be the point A and this one will be the point B. Yeah. So I redraw again this thing here. Okay, so this is the axis X. Okay, this is 2. Right. And this is the origin, and this is our observation point. Observation point. So I will connect the point A and point B, okay, with the observation point, point P. Yeah, right. So we just connect them, okay, and connect them. Okay, so alpha 1, okay, will be this, and this is the alpha 2. And the coordinate here is 2, and this is 0, and this is the unit, this is the vector R, and we know the distance is 5. Okay, so alpha 1, you don't need to find because it is 90 degrees. As for the alpha 2, okay, we can use the tangents. Alpha 2 is equals to 5 over 2. Okay, 5 over 2. So the angle alpha 2 is 68.2. 68.2. So we could replace in our equations. Okay, so the current, okay, the current is 10. Is it 10? Yeah, okay, it is 10. So 10 over 4 pi r. So the r is 5. And then we have a cos alpha 2, which is 68.2 minus cos 90 degree. Okay, as for the phi, it is dl cross unit vector r. Okay, so our current flow in the positive x directions, so it is x cross with the z. Okay, so this one is the r, this one is a dl, cross with the r. Okay, right, so you can start calculate this. So we have a 10. So the answer is equals to 0.059 ampere per meter. Okay, as z you will get negative y. Okay, as z negative y. Y59. So the answer is C. Right. Okay. So Ampere's circular state that, okay, over any closed path equals to the, okay, what enclosed by the path. Okay, enclosed by the path. Oh, this one is the this is the Ampere's law talking about the magnetic field. Okay, so for the magnetic field, okay, Ampere's law is this one, right? Is equals to the I enclosed by the path. So you search for the current, yeah, this is the flux density, wrong. Yeah, this is the current, potential, wrong. So it is a line integral of the magnetic field, okay, over any closed path equals to the net current enclosed by the path. Okay, so the point charge Q, okay, you have the Q, okay, you have a velocity, okay, and you have the directions. This is the directions of the velocity. Okay, the directions of the velocity. Okay, calculate the magnitude of the force exert. So the keyword is the force exert on the charge. Okay, by the field of this one. Okay, so it's calculating the force. Okay, so in this case, you have to apply this formula. Q, okay, U cross with the B. Okay, so this is a formula you have to apply. Okay, so let's put them into the equations. So we have the F equals to Q is 18 nano. Okay, U cross B, you see your U has magnitude and also has directions. Okay, so meaning that your U, maybe I will write it here. Your U will be equals to 5 times 10 power 6. Okay, this is the magnitude. Okay, multiply with this 0.6. Okay, we use this symbol 0.6, 0.75, and 0.3. Okay, 0.3. Yeah. So this one will be your U. Okay, it will be your U. So if you multiply it, it will be 3. Okay, so 5 times 75 is 3.75, and then 1.5. Okay, 10 power 6. Okay, and your B is given. Okay, B is given. So this is U cross B. U cross B. So if you remember how we perform the U cross B, two vector cross product of two vectors. Okay, you can either use calculator or you want to use the manual solution. For manual solution, it will be like this. You have X, Y, and Z. Alright, then you have to put this. This is U, 3.75, 1.5. Okay, and your B is milli. So this one is multiply 10 power 6 and multiply the milli here, 10 power negative 3. Okay, so over here I will just put the value, okay, and 4 and 6. Okay, so this one 18 nano will remain. You remain. Okay, so you do the manual calculations. You can use calculator or you can do manual calculations. Okay, so this one will be 18 so this one will be 18. This is nano, now become micro, negative 6, power negative 6. And you can use calculator to do it. Okay, so let me use the calculator. So I will switch it to vector. We'll switch it to vectors. So for vector A, I divide it as 3 dimensions. So it is 3.75, and then 1.5. Alright, then we go to the vector B. It's 3 dimensions. It's negative 3, 4, and 6. Okay, and then we go to vector calculations. We go to vector A. Go to vector A, cross product with the vector B. Okay, so the answer is, let's straight away write the answer. The answer is 16.5, and then negative 22.5, and then 23.25. Okay, so this one will be your answer. So okay, so they are asking you to find the magnitude. Magnitude. Okay, so magnitude, it means you need to multiply inside. So 18 multiply, so it's 297. Okay, minus 405. So it's 458.5, and this is micro. So you have to square all to get the magnitude. How to find the magnitude? You have to square all, right? So square root the answer, you get 418.5. 418.5. Do we have this answer here? We don't have this answer. This is question number 8. The given answer is this one. And the given answer is this one. I think something wrong with my calculations. I calculate again. Yes, I calculate wrong. The answer should be 6, 5, 6.54 times 10 power negative 4. Negative 4. Okay, so the answer is D. Okay, the answer is D. So this is Newton. Alright, we look at question number 9. Calculate the value of line integral. Okay. Line integrals of magnetic field in closed loop. Okay. For the current and for the currents and closed path in the figure, question number 9. So according to this is the Ampere's law. This will be equals to the current that is enclosed by the path. Okay, so in this case, you can see this L is the path. Is the closed loop. Okay, so the closed path enclose, okay, two current filaments. One is going up 10 ampere, the other is going down. Okay, so the total currents over here will be 10, okay, minus 30. So you will have a negative 20 ampere. Okay, so the total current enclosed by the closed path will be negative 20 ampere. Which of the following statements are not true about the electric force and also the magnetic force? Not true. Okay, E and Fe are parallel to each other. Okay, this one is correct. Okay, when B and Fn are perpendicular to each other. Okay, so this is correct. Okay. Both E and M depend on the velocity of charged particle. So Fm depends on the velocity, but Fe is not. Okay, so this statement is wrong. Okay, it's wrong. So both the Fe and also the Fm can perform work. It means that it can move something. Okay, Fe can perform work, but the Fn cannot. Okay, because the force is perpendicular to the directions. Okay, to the directions of a charged particle. So this one is not true. So you got 2 and 3. So Fm is generally smaller in magnitude in comparison to Fe, and this is the correct statement. So the answer is 2 and 3. Okay, 2 and 3, B. State whether the following statement is true or false. Electromagnetic induction is the phenomena of the productions, okay, of electric current in coil when the magnetic flux linked with the coil is changed. Okay, so this one is the Faraday law, right? So EMF is generated when the magnetic flux change. Okay, so the answer is true. A bar magnet is moving in a steady speed of 0.5, okay, towards a coil of a wire which is connected to a center zero Gauss meter. Okay, so you have a magnet bar. Just imagine you have a magnet bar, north and south, and then you have a coil, right, and that coil is connected to the galvanometers, okay, to measure the currents. So towards a coil, okay, the magnet is now withdraw along the same path at the speed of this one. Okay, going in toward, move toward is this speed, and move out is this speed. So the deflection of the galvanometer is in the, okay, so the same direction as previously, with magnitude of the deflection double. Okay, you just imagine this magnet bar going towards and moving away, withdraw. Okay, what will happen? So the directions, okay, okay, the deflections of the galvanometer will definitely different. Okay, so when it's mentioned about same directions, so this statement is not true. Okay, so opposite direction is correct with magnitude of the deflection half. Okay, so this one is lower than this one. Okay, so which one is correct? So when you move faster, so the deflection will be greater. So the answer is D. Answer is D. Faraday's law demonstrated that whenever a conducting loop connected to a galvanometer is placed in a time-varying magnetic field, an EMF is induced on the conductor. Yeah, that is right. Consequently, a momentary deflection on the galvanometer needle can be observed to exhibit the presence of currents. So which of the following alternative method can be used to indicate or to induce a current on a conducting loop? How to generate current? Okay, in which conditions? Okay, which method can be used to generate current in a conducting loop? By moving the conducting loop into or out the magnetic field. Okay, this is correct. Increasing the number of the turn, of the conducting loop. Which of the following alternative cannot be used? Cannot be used. By increasing the number of turn of the conducting loop. Okay, this is another method to produce the currents. Okay, so this one is not true. You increase the loop number, also useless because you don't have a time varying magnetic field, or you didn't move the conducting loop. By changing the battery to AC source of the coil produced, by changing the battery to AC source of the coil produce a magnetic field. So this one will be a time varying magnetic field. Okay, by changing the area of conducting loop placed in the magnetic field. Okay, so this one is also correct. So the answer will be B. Calculate the EMF when a coil of 100 turn is subject to a flux of this. Okay, flux of this is this one. So the V EMF, the transformer EMF, the transformer EMF will be negative N del over del T. Okay, 3 sin T plus 5 cos T. Right, so you have a 100 turn. So negative 100 multiply 3, you have a 300. Again, this one will become cos T, and plus, no, this one is minus, minus 5 sin T. Okay, so it will be positive 500 sin T, and negative 300 cos T. So the answer is C. Go to 15. Suppose that a straight conductor, okay, 0.1 meter long, move in a uniform magnetic field of 0.5 Tesla. So this is the length. Okay, so magnetic field, Tesla. So this is the B. The velocity of the conductor is this one, and it's direct perpendicular 90 degrees. Okay, to the field. Calculate the induced EMF between the two ends of the conductor when the velocity of the conductor is double. So this one is a motional EMF. Okay, so for motional EMF, the formula will be this one. Okay, so we will have a U, and also the B, and also the L. Okay, so because the U and B, they are perpendicular. Okay, so that the cross product between them will be 1. Okay, will be 1. So U is 5 B is 0.5, and then the length is 0.1. Okay, so this is the motional EMF. But here it says that the velocity is double. Velocity is double. Okay, velocity is double means that is become 10. Okay, double. So what would be the answer? So it's 5 times 0.5 times 0.1 times 2. So you have a 0.5, right? 0.5. Okay. So if a magnetic field given is this one, which of these statement is incorrect? Incorrect. Okay, incorrect. Okay, so this one represent the alpha is over here, 0.1 is correct. Okay, and the beta is over here. Okay, beta is 2, is not -2. And the omega is this one, that is correct. The magnetic field travel along the x directions. Okay, see this is -x, right? So is x direction correct? So the answer is B. So the magnetic field in a certain medium is this one. What type of medium is this? Okay, first of all, you can check. Okay, over here you don't have the exponent. Okay, negative alpha x. It doesn't have the attenuation constants, so it won't be a lossy. Okay, it won't be a lossy. Then it has the beta, and it has the beta. What else do you have? The magnetic field, free space. What type of medium is this? It won't be losses. It can be free space. So which one? Free space. Okay, how to know whether it is free space? Okay, so for free space, the this one, the relationship between the velocity and also the omega would be beta, right? Okay, we can calculate. So if it is 3 times 10 power 8, then it is a free space. This is the speed of the wave in free space. Okay, so let's try. This is 10 power 8 over 0.33. Okay, so 10 power 8 minus what, 0.8. So this is 3, equals to 3.03 times 10 power 6. So it shouldn't be a free space. So it shouldn't be a free space also. And it is not a conductor also. Okay, not a conductor. Okay, so the answer is lossless. It's a lossless. We look at this question number 17. So you have a magnetic field, okay, given. So what type of medium is this? Okay, so you have to guess. So first of all, we look at the amplitude. You can see, okay, the amplitude doesn't contain the exponent term. Okay, it doesn't contain the exponent term. So meaning that it doesn't have the attenuation constant. So this is not a lossy dielectric. We look at the first one, the free space. So when the magnetic field travel in the free space, the speed, the wave velocity will be a fixed number. Okay, that is 10 8. Okay, 3 multiplies 10 8. So here we know what is the beta, and we know what is the omega. So we can link this wave velocity with omega and beta. Okay, so the omega is 10 power 8, and it is 0.33. Okay, you can see what we can get. So it is 3 times 10 power 8. Okay, so meaning that this one will be equals to free space. This is a free space. Okay, the magnetic wave traveling is free space. It is not lossless. and it is not perfect conductor because it matches the characteristic of free space. Which of the following is the characteristic of lossy dielectric? Okay, for lossy, okay, the conductivity won't be 0, okay, and lossy also won't have a conductivity that is infinity, okay. Lossy has a conductivity that is not equals to 0. Look at question number 19. Okay, a manufacturer produce a material with the following characteristic, okay, at a frequency 10 megahertz. So we have to identify whether they are a good conductor or semiconductor, lossy dielectric, lossless dielectric. Okay, so we can straight away eliminate this semiconductor because we never talk about this one. So if you want to know whether it is a good conductor or lossless dielectric or lossy dielectric, we have to look at its characteristic, right? So for different material, we have its characteristic, if you remember. Okay, so for the lossy dielectric, for the lossless dielectric, okay, the conductivity is equals, it will be less than the multiplications of omega and also sigma. Okay, so this is the formula, so we can try. So it is 10 power negative 6. Okay, negative 6. Right, so we can try, okay, whether it is less than that. Omega is 2 pi f. F is a 10 mega. Okay, and it is 5 epsilon naught. Okay, so it would be 2 pi multiplied by 10, it is 10, 10 negative 6, and the answer over here is 10 negative 3, negative 3. Okay, so this statement is valid. Okay, so it means that, okay, it is lossless dielectric. Okay, the answer is D. Okay, in what condition that the attenuation constant is the same as the phase constants? In what conditions? Okay, when the material is a good conductor. Okay, when the material is a good conductor, so this is the answer. Okay, so the other, they are not valid. Okay, you can check the formula. So when in the good conductor, attenuation constant is the phase constants, is the same. Okay, so this is question 20. Okay, so let's look at the subjective questions in part B. So you have a parallel plate capacitors. Okay, parallel plate capacitor. And then this parallel plate has an area of 200 centimeter. Okay, so this is the area. Okay, with a plate separations of 3 millimeter. Okay, so this is the plate separations. So the charge density is this one. Okay, so in this case, you can see that this is a meter square. So this is the rho s, surface charge density, and the A is the dielectric. A is the dielectric. So meaning that over here you have a capacitors. Okay, the A is in between the parallel plate. This is the A with the dielectric constant of epsilon naught. Okay, so first of all you have to find, okay, capacitance. Okay, the first thing is the capacitance. The capacitance. So capacitance is defined as a C equals to epsilon. Okay, surface area divide with the plate separations. Okay, so here, okay, we have a parallel plate with the A as dielectric, so this is going to be epsilon naught, and the surface area is given as a 200 centimeter square. Okay, so you have to take note on this centimeter and also the millimeter here. You have to convert them to meter. So it will be equals to 200. Okay, cm, the c represent 10 power negative 2, and because of the 2 over here, we will power 2 here. Okay, so this will be the area in meter square, and the plate separation is 3 times 10 power negative 3. Okay, so you can calculate the answer. Right, so this is the answer. Okay, we go to the second questions. Calculate the voltage between the plate. Okay, the voltage. So if you remember, the general equations for any kinds of capacitors is equals to C Q over V. Okay, so now in this case, you already know what is the C, right? The C you have calculated in the question number A, and the Q over here, okay, you can find based on the informations of raw X that is given. Okay, so Q is equals to raw X multiplied with the S. S is the surface area. Okay, so when we rewrite them like this, okay, you can easily find the Q. So the raw X in this case is 1 micro, okay, per meter square, and the surface area is 200. We convert it to meter square, okay, and the C is equals to 59.062 picofarad. Okay, pico. Okay, you can calculate the answer. Okay, so this is the voltage. Next we sketch the force between the parallel plate. Okay, so we will sketch the parallel plate first. So one of the plate, okay, has positive charge, the other plate has a negative charge. Okay, so the electric field will be in these directions. Okay, electric field will be in these directions. Okay, as well as the directions of the force. Force in between the parallel plate, because the force has the same directions as the electric field. So you could just label it. Okay, this will be the force between the parallel plate. Next, find the total force with which the plates attract each other. Okay, so now, okay, we have the parallel plate, right? So we have a different charge. So there is a force between them. Okay, so first of all, we have to use the equations F equals to Q over E. Okay, finding the force. Okay, so the Q, okay, you can just imagine the parallel plate is like one is positive charge, one is negative charge, right? So this is the force between them. Okay, so if you want to find the force, for example, at these positions, okay, you have to find the electric field at this position first. Okay, and then you multiply with the Q of the negative charge. This is the Q of the negative charge, right? So same as these conditions. Okay, first of all we find, okay, we find the electric field, okay, contributed by the positive plate at these positions. Okay, if you remember, okay, so the electric field equation for this is equals to rho x over 2 epsilon. In this case, it's epsilon naught because this is A in between terms, okay, in between the parallel plate. Okay, so the rho x is 0.1. Is it 0.1? Sorry, it's 1 micro. Okay, it's 1 micro. 1 micro. Then over 2 epsilon naught. 2 epsilon naught. Okay, so this is the electric field. So you can find the electric field at these positions. Now you multiply with the Q of the negative charge. Q of the negative charge. So in this case, we know the surface charge. The surface charge. And we also know what is the surface area. So from here we can actually calculate the Q. We can calculate the Q. So the Q is equals to the rho x is 1 micro multiply 200 times 10 power negative 4. Okay. So we will have a 200. This is negative 6, negative 4. Okay. We will have a negative 10. Okay. So now you can multiply this one over here. Okay, over here. So the F will be equals to, no, this one we're just talking about the magnitude. Okay, so the 200 times 10 power negative 10 multiply with 1 micro over 2 epsilon naught. Okay, you can calculate the answer. Okay, so the answer is 1. The answer is 1.13 times 10 power negative 3. Okay, so Newton. So this is the answer. Now we look at this question 2. So you have to calculate the magnetic field at the origin. So this is the origin due to the current filament AB as shown in the figure Q2A. Okay, so this is the figure Q2A. So now you have a current filament A and B here. A and B. Okay, so find the magnetic field. Okay, so this current filament is a finite current filaments. So when you want to calculate the magnetic field, you have to use these equations. Okay, I over 4 pi r, okay, cos alpha 2 minus cos alpha 1. And minus, okay, and then you have the phi. Okay, let's search for each of the component one by one. So first of all, okay, you have to search for the R, right? So the observation point is 0, 0, 0. You want to find the magnetic field at these positions. Then you have to minus the position vector of point T. So where is point T? Okay, so point T will be along this line. And when point T, okay, join together with the point observation point P, okay, you will get angle of 90 degree. So this is the point T. So how to do it? Okay, so if you refer to this one, okay, so the X value and the Y value is something that you have no idea, right? but you have idea that the z value will be equals to 0. Okay, so you have to search for the x value and y value. So you can see that obviously this one is at the middle of this line. Okay, middle of this line. Okay, so the point T, the x value will be 0.1 and 0.5 and 0.5, 1/2. Okay, so the answer, okay, the answer will be minus 1/2, 1/2 and 0. Right. Okay, so here your magnitude, okay, your magnitude will be 1/4 plus 1/4, okay, which is equals to 2/4, 1/2 square root. Okay, and this unit vector r, okay, unit vector r will be negative 1/2, negative 1/2, 0, divide with square root 1/2. Okay, so this one will be your unit vector r. Next, we'll be looking at the alpha and also alpha 1 and also alpha 2. Okay, so this is point A and this is point B. Okay, if I draw it again, okay, I draw in this way, easier for you to imagine. So this is point A and this is point B, right? And this is the point T, right? So point T is connected to the point P, your observation point. Okay, so you can do the connections. You see, I always redraw again the figure, because when you redraw again, you can see the alpha 1 and also alpha 2 very clearly. Okay, so this is the unit vector r. So no, this is the vector r, and the length is square root 1/2. This is the length, right? And then from here to here, okay, from point T to point A, this is 1 unit, right? Okay, so you can find the alpha 2 by tangent 180 degrees minus the alpha 1 will be equals to opposite over adjacent. Okay, so you can find the value of alpha 1. Okay, found the value of alpha 1 or tangents square root 1/2. Okay, so 180 minus this, you get 144.74. Okay, 144.74. Okay, and then for the alpha 2, okay, alpha 2 you can get it by tangent opposite, this is alpha 2, opposite over adjacent. So from T, from oh no, sorry, I think my length is wrong. It's from T and it's not 1. Okay. I think I will correct back this one. This one is wrong. See the wrong thing. Okay, so this is wrong. Okay, I have to calculate again. Delete this one first. This one also delete. Okay, you go back again to see this one. Okay, so if you want to know the distance from T to A, you have to calculate it. Am I right? So TA, what is the distance? Okay, so meaning that the A is at the position 0, 1. Okay, 0, 1. And then the point T is 1/2, 1/2. This is when you want to know the distance. Okay. Okay. This is right? So you will get negative 1 over 2, comma, and 1 over 2. Okay, so the length is same as this one, right? 1 over square root 1 over 2. Okay, so this is the length. Okay, the length square root 1 over 2. And this one also square root 1 over 2 if you calculate lah. It's the same thing. Right. This is for the TB. Okay, you can calculate the TB. Is equals to TB is equals to 0, 1. You want to find a length here, and this one. So B is 1, 0. Sorry, TB is 1, 0. 1, 0 minus 1 over 2, 1 over 2. 1 over 2 minus 1 over 2. Okay, so the magnitude is the same as the TA. So it is 1 over 2 square root. Okay, right, you get the length already. Now only we find this, the angle. Okay, so tangent 180 minus alpha 1 is equals to opposite over adjacent. Okay, they are the same thing. Okay, tangents 1 minus 180, you get 135. So the alpha 1 is 135 degree, whereas for the alpha 2, you can see alpha 2 is here, so you know the length is the same thing. So alpha 2 is 45. Okay, you get this already. Right, now I'll turn to the term of phi. Okay, the phi is equals to dl cross with the unit vector r. Okay, we have this, but we have no idea about what is this. This is stand for the length. Okay, length of the current filaments. So you see these current filaments. Okay, it is so the current is flow in these directions. Okay, B to A. Okay, B to A. So B to A, when it is B to A, when you want to find the length, B to A. So the A is 0, 1, right, minus 1, 0. Okay, so it's equals to negative 1, 1. So the magnitude, okay, will be equals to 1 plus 1 square root and equals to square root 2. And then for the unit vector dl, okay, it will be equals to negative 1, 1, and over square root 2. Okay, in our previous example, we don't need to calculate this dl because the current filament is always aligned with the x-axis or y-axis or z-axis. But this one is slightly different a bit. That's why we have to calculate this. Okay, so after getting this one, we can put it here. So negative 1 over square root 2 x, right, plus 1 over square root 2 y. This is your dl. And then cross with the unit vector r. So unit vector r, just now we have this negative 1 over 2, negative 1 over 2, negative 1 over 2, negative 1 over 2 over square root 1 over 2. Okay, this one is the same thing. This is x, and negative 1 over 2 over square root 1 over 2. This is 1. Cross with that. So for the cross product, you need to perform using, you can use your calculator, okay, or you can use the manual technique. Okay, so this one you can check it out. So if I turn it into if I use calculator, so I would like to use calculator, vector air. So the answer is equals approximate to Z. You can use calculator. This one I calculate by using calculator. Okay, you can use calculator to do it. Okay, so now it's time for us to put into all the value that we have into the final equations. So the current is 6 over 4 pi. Okay, and the R is the square root 1 over 2, right? Then we have cos alpha 2, that is 45, minus cos alpha 1 is 135, and behind we have a Z. Okay, so you can calculate the answer is equal to 0.955 Z. This is ampere per meter. Okay, ampere per meter. Now we look at the question B. Again, the question B, determine the total force experienced by the rectangular loop, okay, on the XY plane as shown in the figure. So given you the B is equal to this one. So we refer back to figure Q2B. Okay, you can see there is a square loop. Okay, you have to find the force. Okay, finding the force experience, the force. So now you have how many elements here? You have element 1, element 2, element 3, and element 4. So the F total, okay, will be the summation of F1, okay, plus F2, okay, plus F3, and plus the F4. Okay, so this one will be the solutions lah. Okay, so now what is the formulas for the F? What is the formula of the F? If you want to find the force acting on a current filaments, okay, the general formula that you have to use is this one: integrate I dl, okay, cross with the B. Okay, cross with the B, yeah. Now let's look at where is F1, F2, and F3. Yeah? So I would label them like this. Okay, so first of all, I label the point. This is point A, B, C, and D. Okay, so current flow in these directions. Right, so this one will be F1, this one will be F2, F3, and also the F4. Okay, so we will do it here. I think I will move this. I will move this figure down there. Move them down there. Move here. Right. Okay, so we go to the F1. F1. So F1 is integrate. Okay, integrate from A to B. Okay, the current. Okay, so this element has the length depend on the dy and y. Right. And it cross product with B. B is 6x plus, no, negative, minus minus 9yy, okay, and then plus 3zz. Okay, so you can see here we are going to perform the cross product between these y and the dl and also this. Okay, so to perform the cross product, but this one we cannot use calculator because we have the x, y, z over here. So we are going to do it manually. Okay, so we have x, y, and z. So here we are going to have y. Okay, that is 1 over here. 0, 0. Okay, and then cross with the 6x, negative 9y, and 3z. Okay, the cross product, yeah, the cross product. Okay, so here you have to follow the rules how to do it. So this one will be 3z, 3z, yeah, this is 3z. Okay, 3z, and then minus 0. Okay, minus 0, so you get nothing. So minus, okay, so this one is for the y. Okay, so y is this one multiply this one and this one multiply this one. Okay, also equals to 0. And then plus the z. Okay, talking about the z, then we will be multiply this one minus this. Okay, so it's 0 minus 6,8. Okay, minus 6,8. So it's 0 minus 6x, and this is z. Okay, so when you have this cross product, okay, y cross with the b, okay, you will get this one. Okay, this is y cross with the b. Yeah? Okay, so we put it in. So we have the f. Okay, so a to b. Okay, you can see where is a and where is b. A to b is 2 to 1. Okay, the positions are from 2 to 1, and the current is 5 dy. Okay, then now you put this 3 zx minus 6x z. Okay, so what we could say over here is the z is equals to 0. The z is equals to 0. The z is equals to 0. So you will have this 6x. Okay, we have to know what is the value of the x. So you refer to the line. If this line, this is the line. Okay, so the x is 1. Okay, the x is 1. So you have a negative 30. Okay, x is equals to 1. Okay, and this one will integrate, you get negative 1. So you will have a 30. 30 in the z directions. Okay, in the z directions. This is the f1. Then we go to the f2. Okay, so which is f2? Okay, f2 is b to c. B to c, the force acting on element b to c. Okay, so f2 is a point a, b, c, b to c. B to c. Then we have I, and then we have dx, x, and cross with the b. B is 6x, x minus 9y, y, plus 3z, z. Okay, so this one again we need to perform the cross product. Okay, just like here, it is x cross b. X cross b, so let's do it. X, y, z. So we have 1. This is a 1x. Okay, 1x, 0, 0, and then we have a 6x minus 9y, 3z. Okay, so over here you get the 0x minus, okay, 3z minus 0 and plus negative 9y minus 0 z. Alright, so this is what you get, negative 3z, negative 3zy minus 9yz. Okay, so this one is referred to x cross with the b, x cross with the b. Okay, x cross with the b. Okay, so get this one and replace here. So b to c, okay, you can see the b to c is from 1 to 3 at the position y equals to 1. Okay, so we can put it here. So F2 is 1 to 3, okay, 1 to 3. So for the I is 5, and then we have a dx, then we have this negative 3zy minus 9yz. Okay, so this is 0. So we have the position y, you replace with 1. So it's negative 45. Okay, replace the y with 1. 3 minus 1, you get 2. Okay, so it is equals to negative 90. Okay, negative 90. Z, the directions. And for the F3, okay, we can do it quickly. So integrate F3, see, from 1 to 2, okay, see, from 1 to 2, this is F3, okay, 1 to 2 at the position x equals to 3, okay, 1 to 2, I is 5, and this will be dy and y, cross with the b, cross with the b, so over here, okay, I will just use this one that we have calculated earlier, which is this one, 3zx minus 6xz, okay, three zx minus 6xz. Okay, so whenever you have the z over here is equals to 0. Okay, so the x just now I already mentioned it is equals to 3, right? So you have negative 30, then you multiply with the 3, okay, and integration to 1, you get 1. So it's minus 90 z. Okay, and lastly is the F4. So for the F4, the length, you see you integrate the length. F4 is here. Okay, integrate from 3 to 1 at the position y equals to 2. 3 to 1, 3 to 1. Okay, so at the position x. Okay, so this one is x cross with the b. So x cross with the b, I will use back the cross product that we have calculated before, x cross b. Okay, so x cross b will give you 5. And here you have a dx, then multiply negative 3zy minus 9yz. Okay, so over here is equals to 0. So here you have negative 45. Okay, and then the position here, just now the position is what? Is 2, right? The y value is 2. Okay, integrate this thing, you get negative 2. So it's equals to positive 180 Z. Okay, so you can see what is the answer for each of them. 180 minus 90. Okay, minus 90, you get 0 already. Okay, you get 0 already. And here, you see, you have a 30. Okay, 30. So the total will be 30. Yeah, just add all of them. F total, add all of them, and there are 30 Z Newton. These are directions. Okay, for the total force. Now we will look at this question number 3. So you have an inductor and is formed by winding ends of thin conducting wire into a circular loop of a radius of 10 centimeters. So here you can imagine how your loop looks like. Okay, so it is a circular loop. Okay, circular loop. So this is your loop. Okay, circular loop. Okay, so the turn is N and the radius is 10 centimeter. Okay, so 10 centimeter cm. So the inductor is in the xy plane. Okay, so you can just imagine this is the xy plane. Okay, I will label here as y, label here as x. You can imagine. So connected to a resistance of 1000. Okay, and it can be seen in figure Q3. Okay, you can refer to Q3. Okay, but Q3 something like this also lah. So in the presence of a magnetic field, okay, so now you have a B equals to 0.6 sine 10 power 3 T Z. Okay, the current is induced. Okay, this is the I induced. The I induced. They give you the I. Find the number of turn here. Okay, they ask you to find the number of turn. Okay, so you know that when you have this condition, when you have a loop of wires and then you have a time varying magnetic field, so you are going to generate the transformer EMF. Okay, so this is the equation for transformer EMF, right? So integrate B dot ds. Okay, so this is the formulas. So they tell you that the I is this one. The I is given. Okay, you can get the I, okay, by divide the voltage, the transformer EMF voltage with the R, right? So this is the formulas, meaning that they give you the transformer EMF through the calculations. Okay, and then all you have to do is to find the N. You have to find the N, right? Okay, so what you have, first of all, I think you need to find what is the transformer EMF first. Okay, so the I, okay, so the transformer EMF is equals to I multiply with the R. Okay, so the I is given by the questions, which is a 190 cos 10 power 3t. Okay, and it's a milli, I see, milli, okay, milli, milliampere. So milli, if I convert 1 to 3 is 0.19, okay, 0.19, okay, I straight away convert that. Multiply with the R, so the R is 1000, right? Okay, so it is equals to 190, okay, cos 10 power 3t. Okay, so this is the EMF, alright? Okay, so this EMF, we are going to replace it over here, okay, and try to calculate this thing, okay? So you can get what is the value of the N, right? Okay, so for this one, okay, integrate B dot dx, let's try to find out. Okay, so what is this? Okay, so the flux they're coming out from the loop. Okay, loop of wire will be integrate the B. What is the B? The B is 0.6 sine 10 power 3t. Z is the directions of the B, and dx. Okay, x stands for the surface, the surface of the loop. Okay, you can see this is the surface of your loop. Okay, circular loop. Okay, so the dx that you will be using the cylindrical dx, cylindrical coordinate system dx. So you have a r, dr, d theta. Okay, and it is in the z directions. So as the result of dot product, you could get this one is equals to 1. Okay, and for the double integral, you are going to define the r, which is from 0 to 10 centimeter, which is 0.1. And then the theta will be 0 to 2 pi because it is a circle, okay, dt. So what you will get over here is the 0.6 sine 10 power 3t. Okay, this is a constant. So if you press calculator for the integration with respect to the r, so you will have this one from is equals to 5 milli. 5 milli. When you integrate the r, okay, you will get 5 milli. Okay, I will write down 5 milli. Okay, and then for the theta, it will be 2 pi here. Okay, 2 pi. Okay, next you have to perform the differentiation with respect to the t. So first of all, I combine all the value first. 0.6 times 5 milli, okay, times 2 pi. So I want to combine them first. 0.019. Okay. Okay, so differentiate with respect to the sine. Differentiate with respect to the t. Okay, for sine, you will get cos 10 power 3 t, and then okay, 10 power 3 over here. Okay, so times 10 power 3, right? So you will get something like 6 pi or 19. 1, 2, 3, right? 19. 19 cos 10 power 3 t. Okay, so this one is this one. This is this one that I asked you to calculate. Okay, so you see, you can compare. So now I put it together. Okay, 190, okay, cos 10 power 3t is equals to negative n. All right, so this one is a 19 cos 10 power 3t. Okay, so this one, what I'm writing over here is the V transformer equals to negative n, okay, dt integrate v dot ds. So this is what I'm doing. Okay, you need to find out this thing. Okay, so obviously you need to compare the terms over here. Okay, the values here, right? Okay, how to make the 19 become 190? This is easy, right? Okay, so from here you can know that the n is equals to 10. Okay, so don't worry about the negative. The negative is telling you something related to the current flow in the loop. Okay, current flow in the loop. So you don't need these things. Okay, so the n is equals to 10. Okay, so this is the answer. Suggest a method to obtain the induced current of 95. Okay, 95. You see, it is actually, just now we have a 190, right? 190 now become 95. Okay, how to get this 95? You see, this one to this one. What we can do to get this become 95? Okay, so a method. Okay, so you know this thing is directly, okay, current directly related to the R, right? So one of the method is to change your R. You can change the R connected to your things. Okay, so you can propose. So if you want to get 95, how to get? So V equals to IR. Okay, This is transformer EMF over R, right? Okay, so if you want to find the R value, okay, so the V value is fixed, which is 190 cos 10 power 3t over the I, right? I now you 195 cos 10 power 3t. So you can cancel this thing. So you take this 190 divide with the 95. So the resistance now is 2. So you can change, okay? Change the R to 2 to get your I is equals to 95 times cos 10 power 3 t. Okay, so this is one of the way of doing it. Okay, so is there any other way for us to do it? Okay, can we change the turn? This is the first way. Okay, so can we change it? Okay, so we can also change it by changing the n, right? Okay, so if you want to maintain the R is equals to 1000, okay, for example, the R equals to 1000, okay, or alternative, this is alternative. If I want to make my I is equals to 95 cos 10 power 3t, and I want to maintain my R is equals to 1000. So what you can do is you have to generate a different level of the transformer EMF. Okay, V equals to IR. Okay, so you will have 95000. Okay, cos 10 power 3t. Okay, so you are going to generate this. Okay, so if you put this thing together with this is 95k cos 10 power 3t equals to minus n. Alright, so just now we have this one, right? Okay, so this one you can remain 19 cos 10 power 3t. Okay, so try to find out what is the value of the n that is suitable. Okay, so you can cancel this to find the n, right? Okay, so the n is equals to 95 divide with 19. Okay, so it can be 5000. 5010. Wait. This one should be milli, I'm sorry, this one should be milli. So when milli multiply with 1000, you get 95 lah. There is no more k. Okay, so this one will be 5. Okay, will be 5. This is milli. I missed the milli. Okay, so this one should be the correct one. Alright, question number 4. So you have a uniform plane wave, okay, and this plane wave is propagating in the x directions of free space, okay, right, so this one is telling you the k, okay, the electric field is polarized in the y direction, so this is the directions of the electric field, sinusoidally with maximum and minimum values of 1. Okay, so this one is the amplitude, right? Amplitude. Okay, occurring at x equals to, it's not amplitude. Okay, so this value, it's amplitude, maximum and minimum value, occur at x equals to 30 meter and x equals to 100 meter respectively, and the E, okay, at position 0 and time 0, okay, position 0 and time 0 is equals to 0. So calculate the wavelength. Okay, so first of all, I think you need some drawing to give you some idea. Right, first one is about the amplitude, right? Okay, it's asking us to find the wavelength. Okay, so first of all, what is wavelength? Okay, so wavelength is the distance, okay, for a sinusoidal waveform to complete one cycle. Okay, so just now it mentioned that the maximum is 1 and -1, right? 1 and -1 at the position 30 and 150. At the position of 30 meter and 150 meter. This is 150 meter. Okay, this is the minimum. So if you want to find the wavelength, okay, so from here until here will be half of the wavelength. Am I right? Half of the wavelength. So if you want to calculate the wavelength, it will be 150. Okay, lambda is equal to 150 minus 30. Okay, this one will be the half wavelength. And if you multiply 2, it will be the full wavelength. Okay, so it is equals to 120 multiply 2 and equals to 240 meter. So this one will be the wavelength. Okay, wavelength. And the B, phase constant. So questions number B, you are required to find the phase constants. Okay, so the formula for the phase constant is equals to 2 pi over lambda. Okay, you just get your lambda, right? So 2 pi over lambda is 240 meter. Okay, so the answer is equals to 0.026. Okay, this one is your beta, the phase constant. And C is the angular frequency. So angular frequency is the omega. It is equals to 2 pi f. Okay, 2 pi f. Right, so if you, beside using these equations, you can also use the other equation, that is omega equals to beta multiplied with the C. C is the speed of the electromagnetic wave in the mediums. Okay, so you get this 0.026 multiply with 3 times 10 power 8. This is the speed of the electromagnetic wave in free space, and you get 7.85 mega. Okay, mega. So this is the angular frequency. And then for the D, okay, you have to find the equations of the electric field. Okay, so the equations of the electric field, okay, will be equals to, of course, you will have amplitude, right? So you can write whether it is sine or cos, because it's not specific in the questions whether it is sine or cos. You can put sine or you can put cos. So you will have omega t. Okay, and from the question we know that the k is equals to the x directions. Okay, so you will have negative x. Okay, x directions. Okay, and the direction of the electric field is y. Okay, this is what the information from the questions. Okay, so okay, right, forget that. This one might be, you can put the angle in case you have a phi. You have the phi. Okay, so question tells us that the electric field when the x is 0, t is 0 is equals to 0. Okay, what happens over here when the x is 0? Okay, when the x is 0, okay, when the x is 0, it is sine. Okay, t is 0, so 0, x is 0, 0. Okay, so plus the phi. So plus the phi. So in order to make this thing to be 0, okay, make this thing to be 0, okay, it must be sine 0. Okay, sine 0. So here also means that the phi is equals to 0. And the phi is equals to 0. And of course, you can replace the A with 1, right? The amplitude given by the questions. Okay, so from here, we can put the value of the electric field into it. Okay, is 1 sine omega t. okay, 7.85 mega, t minus 0.026 x and y directions. Okay, so this one would be the electric field formulas. Okay, next one, the E when the x is 120 and the t is equals to 2 microseconds. So this is easy. Okay, you just replace the value. Okay, so E is equals to 1 sine. So you multiply this at 5 mega with the t is 2 micro minus 0.026. Okay, and the x is 120. Okay, y. So this one take notes, yeah. You have to set the angle to be radians for you to get this answer equals to negative 7.96 millivolt per meter. So this is the electric field at these conditions. Alright, so next one we will have to find the expressions of the magnetic field. Expressions of the magnetic field. So the magnetic field will have a similar equation as the electric field, except for its magnitude, right? Magnitudes. So this is t minus this one also the same, and also the directions. Okay, so you need to find out the directions and also the magnitude. First of all, let's look at how to find the directions of the magnetic field. You can use this relationship. So you have the directions of the E, and you don't have the direction of the H. The direction of the K is equals to X. Okay, so here you will get YZ. Okay, YZX. Okay, the direction of the H is Z. Okay, you can put it here. Now next one is the amplitude. Okay, so the electric field magnitudes over the magnitudes of the magnetic field will be equals to the eta. Eta is the intrinsic impedance of the mediums. Okay, so if you look at this medium, it is a free space. Okay, so for free space, so the eta is a fixed value, okay, which is 377. Okay, 377, it is a fixed value for free space. Okay, so from here you can calculate, okay, your H is equals to 1 over 377. Okay, so you can put 1 over 377 over here. 1 over 377. Okay, this is the amplitude of the magnetic field. Okay, right. Next one, justify whether the electric field experience amplitude reductions. Okay, amplitude reduction means that when it oscillates, okay, the amplitude is getting smaller and smaller, smaller and smaller. Okay, so this is the amplitude reductions. So this depends on whether you have the exponent terms, okay, in your magnitude. Okay, so in this case, our E, you see, we don't have the exponent terms here. Okay, because it is free space. Free space, we don't have the attenuation constants. Okay, so you can write down that, okay, the electric field, the E field, does not experience amplitude reductions. Why? Because it is propagate in free space. Okay, in free space. Okay, and there is no attenuation loss. Attenuation constant, I would say. Attenuation constants. Okay, which means the alpha is 0. This is the why the electric field doesn't experience the amplitude change when it propagates in free space. Right, so this is the solutions for this final exam.